Yeah. Can you hear me and can you see my screen?
Yeah, I can hear.
Okay, great. And you can also see my screen, right?
Yes, yes.
Oh, okay, great. Okay. Okay, so as we get the recording, okay, yeah. Okay, so welcome to week 5 problem solving session for circuit complexity. Today we'll solve some problems related to week 5 assignment and then we'll also discuss week 4 assignment. But before we start solving problems, let's quickly recap what we did this week. So this week we saw the proof of the theorem that division of two n-bit numbers is in log space uniform NC1. We saw the definition of the class NC1 last time, and this week we also saw what log space uniform NC1 is, right? So log space uniform function family is in log space uniform NC1 if number one, it is an NC1 circuit family, and number two, that family can be generated by a log space Turing machine, right? Yeah, so that was the definition of log space in uniform NC1, and we saw that division is in that class. So now let me quickly recall the proof outline that we saw. So the way we did was, so we sort of broke up the proof in two parts. The first part, we showed that division is NC1 reducible to powering. And then the second part, we tried to show that powering is in NC1. Okay, and what do I mean by NC1 reducible? Uh, so division is NC1 reducible to powering means that there is an NC1 circuit which can compute division, but this NC1 circuit is not like your usual NC1 circuit. It's a special type of NC1 circuit which has oracle gates which can do powering. So, for example, it can have a gate like this. If I feed in x, it would output, let's say, x to the k for some k. Okay. So division has an NC1 circuit with powering gates in it, and all these powering gates are sort of called parallelly. So there was just one layer of powering gates, and so if we were to show that powering is also in NC1, then we could replace all those powering gates with NC1 circuits for powering, and then we would still have an NC1 circuit for division. Okay, so once we have proved lemma 2, all we have to do is to show that powering is in NC1. And while we did not use it for the proof, we also saw converse of lemma 2. That is, powering is also NC1 reducible to division. This we don't need for the proof, but it's nice to know. Okay, so once we have proved lemma 2, we need to show that powering is in NC1. And what we tried to do was something a little more general. We tried to show that iterated multiplication, that is x1 to x, multiplying x1 to xn, is in NC1. And observe that powering is just a special case of iterated multiplication, right? For example, in powering, all of x1 to xn are exactly the same. And the idea was the following. So we want to compute x1 to xn. So we would find small numbers c1 to cm. The bit complexities of c1 to cm would be like log n, such that their product is strictly greater than the product of x1 to xn. And then we would show that for all I, x1 to xn mod ci can be computed in NC1. And then we would use the Chinese remaindering theorem. So what Chinese remaindering theorem tells us is that if you have something like this, then from this you can compute x, which is a product. And towards this, we first showed that for any prime power p to the L, strictly less than n, where n is the size of the xi, the product of x1 to xn mod p to the L can be computed in log space uniform NC1. So, so for the idea to work, we need Ci over here, but right now we have just p to the L. Yeah, and we'll slowly move towards Ci from P to the N. But before that, let me recall the Chinese remaindering theorem. So in the Chinese remaindering theorem, we have C1 to Cm, which are relatively prime. And for all I in M, Yi in Ci minus 1 is such that the GCD of Yi and Ci is 1. So Yi and Ci are relatively prime as well. Then the theorem says that there exists a unique X in C1 to C1 times Cm minus 1, so that for all I in M, pi equals to Yi mod Ci. So if you were to replace this Yi with x1 to xn mod Ci, you would get x as desired, right? Yeah, so we also saw that the y in the CRT can be computed in log space uniform NC1. So we have that we can compute this mod PL, and we know that if instead of PL we had CI, then we could also compute the product itself using lemma 3, right? So all we have to now do is somehow replace P to the L by Ci in this lemma, and that we'll do in the next class. So let me just tell you what we'll do in next class. In the next class, we'll show that how we can find C1 to Cm such that the required condition, that is C1 to Cm greater than x1 to xn, is satisfied. And we'll also see how, given such C1 to Cm, we can factor so given such C1 to Cm, we will factor each of them. So each of the Ci's would look like Pi to the L's. Then we can use lemma 2 plus lemma 3 to compute x1 to xn mod Ci. And then we can again use lemma 3 to obtain x1 to xn. Yeah, so this is sort of the overall proof idea of this theorem. Yeah, so before we move on to problems, if you have some question about the proof idea, you can ask now. Okay, so if there are no questions, then let's move on to some problems related to this week's assignment. So the first one is this. Prove that NAND NOR and XNOR can be computed uh, threshold gates. So TH, okay, using threshold gates. Okay, so we want to show that NAND, NOR, and XNOR can be computed using threshold gates. And okay, one way to do it is, let's say, so in the class last week, we saw that and OR can be, and OR and NOT can be computed using threshold gates. So one way to show that NAND, NOR, and XOR can be computed using threshold gates is to just use those facts, right? But what we'll do is we'll try do something more explicit. What we'll do is we'll come up with explicit constructions. So we'll so what we'll so okay, what does the threshold gate looks like? It is parameters by a1 to am and theta, so that the output is 1 if and only if the sum over ai xi is greater than theta, right? So what we'll do is for NAND, NOR, and XNOR, we will construct these ai's and thetas. Okay, so let's start with the NAND gate. So the truth table of NAND gate looks like this, right? So NAND is the negation of AND. So it's going to be 1 only when AND is 0. And we know that AND is 0 in all these three cases. So NAND is going to be 1 in all these cases, 0 in the last one. Okay. So from this truth table, uh, can you find a linear relation? Okay. Can you tell me what some, okay. Can you tell me when would this, so can you tell me the values of A, B, and theta such that we, we would get NAND? Okay, so when is NAND 0? NAND is 0 if and only if X and Y are both 1, right? So uh, we can write the following: uh, 0 if and only if x plus y is greater than equals to 2, right? And so it means that NAND is 1 if and only if minus x plus y is less than or equals to minus 2. And so it's 1 if and only if minus x minus y. Oh, wait, okay, so what do we want? We want a, b, and theta so that ax plus by less than equals to theta implies NAND is 1, right? And what do we have? We have that 0, NAND is 0, if and only if this is true. So NAND is 0 if and only if I multiply by minus on both sides, I get minus x minus y is less than equals to minus 2. And so if I negate both sides, I get NAND is 1 if and only if x plus y is less than equals to 2. Right? Yes, I messed up the previous time. And this means that NAND is 1 if and only if minus x minus y is greater than equals to minus 2. Right? And this naturally gives you the TCO circuit command, right? So you can define threshold x comma y as 1 if minus x minus y is greater than equals to minus 2. That is a1 is equal to minus 1, a2 is equal to minus 1, and uh, theta is equal to minus 2, and 0 otherwise. And for this threshold, for this particular threshold gate, you would have, so is this fine?
Yes.
Yeah. Okay, so the next is for NOR, so I think you can try this now. So again, let me write the truth table. Okay, so NOR is the negation of OR, so it would be 1 only when OR is 0, right? And OR is 0 in only this case. So this is 1, everything else is 0. Yeah, so can you come up with something like this or this from the truth table? Like you only seen it once, so maybe you can try it this.
I think in case of NOR, we can focus on the first row.
Right.
So,
Yeah, so it's 1
I mean,
if and only if.
A would
Yeah.
be 0, B would be 0.
Oh, A and B can't be
Uh,
0, right? So if A and B are 0, your input to the threshold gate is always going to be 0. So what are
oh,
A and B? It's AX plus BY, right?
yeah.
So your X and Y would be 0 if you are focusing on the first row. But you want to come up with A and B so that if you multiply A2 0, B2 0, uh, it has some relationship with threshold, which you also want to find out, right?
Yes, yes, yes. A and B can be any numbers actually.
Okay, and then what do you want the threshold to be?
One,
Okay, so what you are saying would work for just the first row. So AX plus BY is greater than equals to, sorry, less than equals to 1 would work for the first two, right? Because no matter which values of A and Y you pick, it's always going to be less than 1,
yes, yes.
right?
Yeah.
But suppose B were minus 1 and A were 0, right?
Hmm.
Then even for the second row, your condition would be satisfied, right? Because AX plus BY would be minus 1, which is less than 0,
Yeah.
right? So you want to find something that works for this, but not for these three, right?
Yes, yes.
Right. So you have the correct threshold. Now, can you come up with the correct values of A and B? Okay, so in the counter example that I gave you, B was minus 1, right?
Yeah.
And it was that minus sign that was hurting us, right?
Yes.
Yeah, so using this, can you suggest possible values of A and B? So we know it can't be 0, and we know that B can't be negative. Yeah.
I mean, 1 minus 1. No.
Okay, 1 minus 1. Okay, 1 minus 1 would cause an issue over here, right? It would work in these two cases.
Yes.
Okay, so first of all, this is sort of symmetric, right?
Mm-hmm.
So here X and Y are sort of indistinguishable, right? It doesn't matter if I switch these two,
No.
right? So if you are suggesting 1 for X, why not try 1 for Y as well, right? Why are you trying to keep A and B different? If you just do this, then it works, right? X plus Y less than equals to 1,
Yeah.
right? And okay, but for threshold, we need to do an equals to, so we can say this is minus X minus Y greater than equals to minus 1. Yeah, so now we can do this, right? Uh, hmm, and now threshold for Y for this beautiful graph is no. Okay, so is this fine?
Yeah.
So now let's try Axonor. That would be slightly different. Oh, let me add a page. Okay, so I don't have enough space for the truth table over here. So let me just write it next. Okay, so we again. So XOR is one if and only if sorry, if and only if both X and Y are the same, right? So it's this. Okay, so now can you? So this is slightly difficult, but can you come up with A and B so that something like this holds? Yeah, first of all, is it even clear that you can come up with such A and B? Such A and B exists. Because over here, in both these two cases, it was pretty simple, right? We had 1 0 or 1 1. So we could just focus on that row and we were fine, right? But over here, you have two ones and two zeros. Now, it shouldn't be difficult to come up with a condition like ax plus by greater than equals to theta for each of these rows. But then what? You will have two conditions. Yeah, instead of just one. So do you see the problem over here?
Yeah.
Yeah. Okay, so and one way to resolve this is okay. We know that OR is computable by a threshold gate, right? So instead of just coming up with one threshold gate that computes X naught, we can come up with a circuit containing three threshold gates. Okay, one threshold gate would give you one if and only if this is one. One threshold gate would give you one in this case, and then you would OR them, right? So what you can do is create three threshold gates. Okay, so for this row, uh, it's one. Okay, so for this row, the relevant condition is one when Okay, so what's the relevant condition over here? And it's x plus y less than equals to 0, right? Which is the same as minus x minus y greater than equals to 0. And what's the relevant condition over here? It's 1 if and only if x plus y greater than equals to 2. Right.
Yes.
Yeah. So what we can do is define two threshold gates, TH1 and TH2, and then uh, x naught, right? So is this fine?
Yeah.
Yeah. So now, yeah, just to get a complete circuit using threshold gates, let's also quickly recall what we saw, the threshold circuit we saw for all 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1. Yeah, so what's the like relevant expression over here in terms of A and B? So over here there is just 1, 0 over here, right? So we can just focus on that. So 0 is then only greater than equals to 0, right? And if you observe, this is exactly the gate TH1, right? So we can compute X naught like this. Yeah. So is this fine?
Yeah.
Yeah. Okay. So then let's look at the next problem. Uh, so next problem is to prove that threshold. Yes, we want to show that we can uh, like compute so any threshold function in NC1. Okay. Okay. So it's a general threshold function. So what does this look like? So any threshold gate is parameterized by these things, right? One when a1 x1 plus. So we have a1 to an and theta, and we want to. Okay, so what does the threshold gate do? So given a1 to an and theta and x1 to xn as input, the threshold gate first computes this and then makes this comparison, right? So we want to do these two things in NC1. So so this would be our approach. So is the approach clear?
Yeah.
Yeah. And okay, so First, we want to compute sum in NC1, right? So we saw something in class related to this. So we saw in class that something about computing this sum. So what's the complexity of computing this sum?
I think logarithmic depth
Right.
and
So that's
polynomial size.
right. So that's exactly NC1, right?
Yeah.
So we can compute this sum in NC1 and then make this comparison. So we'll have to see how to make that comparison in NC1, right? However, instead of doing it like this, I'll do it in a slightly different way because uh, if I do it like that, the comparison becomes much easier. Okay. So like the issue with this approach is that okay, this sum might become negative, right? So then okay, so this there are four possibilities. This is positive, this is positive, this is positive, this is negative, this is negative, this is positive, and both are positive, right? So while comparing, you also have to take care of the signs. What I want to do is somehow get rid of the signs. That would make comparison much easier for me. Okay. So instead of computing this sum directly, what I'm going to do is I'm going to write this sum as plus a0 where a0 is minus. Okay. So let me write it. Yeah, so first we'll write it in this form and then let me call this entire thing B1, Bn, and B0. Okay, so then this is 1, rather let me B0 plus up to Bn is greater than equals to 0, theta, right? Sorry, 0, yeah. Theta is 1. Okay, so now what we can do is the following. Okay, now one way to do it would be just sum them up and check if the sum is positive or negative, right? But again, you still have to worry about the sign of the sum. So there is a better way to do this, and it's the following. So let S1 be the subset of P0 to Bn containing uh, non-negative numbers, and S2 be the subset of P0 to Pn containing negative. Okay, then even x1 plus say minus. Okay, so what we've done is divided B0 to Bn into two sets, S1 and S2, one containing just no, 0 and positive numbers, and another containing negative numbers, right? Then we can move all the negative numbers to this side. So we get sum over B in S1 and sum over B prime in S2, but minus B prime. But minus B prime is positive, right? So now we have a positive number over here, we have a positive number over here, and you want to compare their sums, right? So now we don't have to worry about signs at all. Okay. So is this fine?
Yes.
Yeah. Okay. So once we have this, we can. So here's the thing. So step one is compute. Okay, let me call this A1. Okay, this can be done in NC1, right? So now what we want to do is we want to compare these two numbers, right? And we want to show that that can be done in NC1. So first of all, what's the bit complexity of A1 and A2 have at most? So how many bits do A1 and A2 have at most?
Uh,
Okay, so both can be at most sum of n plus 1 many numbers, right?
yeah.
And each of those numbers are, let's say, n bits.
Mhm.
Okay, so what happens when you sum up uh, m numbers of n bits each? How large can the sum be?
I think at most n plus one.
Not exactly. Okay, so you have m numbers. Each and every one of them is n bits, right? So each and every one of the numbers is less than 2 to the n, right?
Yeah.
And when you sum them up, the sum is at most m times 2 to the n, right?
Okay. Okay.
Yeah,
Yeah.
so it's like
Yes.
n plus log m. But okay, let's not worry about it. Both of them are, let's say, like just poly n bit numbers, right? Okay, so now you have two. Okay, let me make this little more space. So you have two m-bit numbers, and you want to compare them using log depth circuit. So how can you do that? Okay, so when is okay? So you want to compare A1 and A2. So when is A1 greater than or equals to A2? Like, can you give me a bit by bit condition for this? So let's say A1 uh, is Cm minus 1. Oh, it should start with a minus 1. And let's say A2 is dm minus 1. So these are the like binary representations. So can you tell me what conditions should Cm minus 1 to C0 and dm minus 1 to d0 satisfy so that A1 is greater than or equals to A2? Okay, so suppose A1 suppose Cm minus 1 were strictly less than dm minus 1. Then can A1 be greater than equal to A2? Okay, let me make this little simple. So instead of let me say it like so let me say that A2 is this quantity. Okay, A2 is this sum plus 1. So now okay, so we have this sum. So A1 x1 plus if and only if Okay, so A2 is now this one, so it's one added, right? So uh, this greater than equals to this means that, okay, wait, no, let me subtract one. Yeah. Okay, so we want to compute this, right? And that would be true if A1 is strictly greater than A2. Why? Because, okay, LHS is greater than equals to RHS means LHS is strictly greater than RHS minus 1, right? Yeah. So we have just these two numbers and we want to check if A1 is strictly greater than A2. Now, this is much simpler than A1 greater than equals to A2. So now can you tell me the bit by bit relationships to hold that should hold for this to happen?
Maybe each bit is strictly greater than the other one.
Yes, so that's a good start. So, okay, what you are saying is, let's say Cm minus 1 is strictly greater than Dm minus 1, right? But,
Yeah.
okay, so what about these two numbers, 1, 0 and 1, 1, 1 and 1, 0? So the first bits are exactly the same, right? But the number are still like different, right? So 1, 1 is greater than 1, 0. So you are right. You would ultimately require something like this, but not for every bit.
Hmm.
Okay, so the claim is this. So A1 is greater than A2 if and only if Cm minus 1 is greater than Dm minus 1 or Cm minus 1 equals to Dm minus 1 and Cm minus 2 is strictly greater than Dm minus 2 or Cm minus 1 equals to Dm minus 1 and Cm minus 2 equals to Dm minus 2 and Cm minus 3 is strictly greater than Dm minus 3 and so on all the way up to Cm minus 1 is the same as Dm minus 1 and Cm minus 2 is the same as Dm minus 2. Yeah, so what this condition is saying is that either the first bit of A1 should be greater than the first bit of A2, or if they are the same, then the second bit should be greater. If the first two bits are the same, then the third bit should be greater, and so on, right? All the way up to if C1 to Cm minus 1 and D1 to Dm minus 1 are the same, then so on, or they should be 0. Then C0 should be greater than D0, right? So what we are doing is we are starting from here and going in this way and saying that at least one of the bits should be greater, right? So, first of all, are you convinced that these two are exactly the same? This and this?
Uh, Actually,
Okay, so,
I don't know. Maybe I'll have to work out.
okay, so maybe I can show you some examples. Okay,
Yeah.
yeah, okay. So, let's see 1, 1, 1 and 0, 1, 0. So, 1, 1, 1 is greater than 0, 1, 0, right? And over here, this condition is satisfied, right? That the first bit is larger. Okay,
Yeah.
right. Now, 1, 1, 1 is also greater than 1, 0, 0, right?
Yes.
But over here, the first bits are the same and the second bits are different, right? And the second bit over here is larger.
Yes.
And 1, 1, 1 is also greater than 1, 1, 0, right?
Yeah.
Here, both the first two bits are the same, and the third bit over here is larger than the third bit over here, right?
Yes, yes,
So now you can see if that if you have m many bits, you have to basically first check are the first two bits the same? Okay, is the first bit of A1 greater than the first bit of A2? You are done. Otherwise, check so first bits are the same and the second bit of A1 is larger than the second bit of A2. If this, you're also done. Otherwise, check if the first bit of A1 and A2 are the same, the second bits are the same, but the third bit of A1 is greater than the third bit of A2 and so on, right?
yes,
And even if one of these conditions is satisfied, you are done, right?
yes,
So over here we have these conditions in the brackets, and we want one at least one of these to be satisfied, so we can put or in between, right?
yes,
And that gives us this RHS. So is it fine now?
yes, yes.
Yeah. Okay. So now we want to compute this in NC1. So we have m many brackets, right? So uh, m minus one and yeah, let me just write order n and order log n. So, first of all, let's focus on how we can compute all of these brackets. We'll worry about how to compute the brackets later. But okay, how many brackets are there? M many, right? So you have M many inputs and you want to compute their OR. So what you can do is you can just create a tree of OR gates of depth order log M and that would compute the OR, right? So is this fine?
Yes,
Yeah. So now we want to compute each bracket, right? So each bracket is an AND of at most M many functions on two bits, right? Yeah, so let's look at this AND, which is the largest. So it's an AND of M many functions, each on two bits, right? These are the M many functions.
yes,
Each of these functions can be computed by a constant size, constant depth circuit, right?
yes,
So we don't need to worry about the functions. We just need to worry about computing that AND, right? So each function, so again, it's similar to the OR that we did before. So we want to compute AND of M things. So we have M inputs. We can just construct a tree of AND gates, right?
yes,
Yeah. So the total size is equal to order one for the functions plus order M for the AND tree and order Oh wait. Okay, so it's order one for each of these functions, right? But within an AND gate, there can be m many such functions, right? Plus order m for the AND gate. So this is the size that we require for one such gate, right? So one such bracket. Is this fine?
Yes.
And how many brackets are there? M many, right?
Yeah, M brackets.
And
Yeah.
an additional order m for OR, right? So it's like order m squared. And what about depth? So it's order one for the uh, uh, those functions on 2 bits plus order m for the AND gates plus order m for the OR gates. So over here we don't have to do something like this because all of this is happening in parallel, right? What you can do is like compute this all the brackets in parallel, and inside the brackets you can compute all of these in parallel, right? So you just need to add up all the bits. Oh, sorry, order log n everywhere. So is this fine?
Yes.
Yeah. Yeah, so we have a circuit of size order n square and order depth order log n, but m is like poly n. So this is like order poly, size is order poly n, and depth is order poly of log n, which is order log n, right?
Yes.
Yeah. So size is, yeah, and so we are done, right? Because we have a poly size log depth circuit, that's NC1. So is this fine?
Yes.
Yeah. Okay, so now let's so show that this function having n comma d defined as all strings x of all strings x of length n such that their Hamming weight okay, see, we want to show that the line the function which outputs one if and only if the input is a string of Hamming weight one, sorry, Hamming weight d, exactly d is in TC0. So is this function clear?
Yeah. I
Yeah,
mean, the sum of the bits is exactly D.
exactly d. Right. Yeah, and
Yeah.
okay, so that okay, yeah, so that sort of gives you a circuit, a TC0 circuit, right?
Yeah.
Okay, so like can you specify how you would get a TC0 circuit from that?
I think this function can be thought in terms of threshold.
Right. So okay, can you tell me how would you think of this in terms of threshold? Uh, in the meantime, let me write this. So number of pixels which are one is exactly d, which is the same as sum over I x I. Okay, so we have this. Now, how can we convert this into a threshold game,
So we can choose a1 to an as 1
right?
and theta as d.
Okay, so
Uh,
that would output one whenever the Hamming weight is at least d, right?
at least d, yes,
Here
yeah,
they want exactly d.
exactly. So both maybe greater than equal to and less than equal to.
Yes. Yeah. So, and yeah. And okay, so this is in the form of a threshold gate, but this isn't, right? So how can you convert this into a threshold gate?
Negating.
Right. So it's sum over I xi greater than equals to d and sum over I minus xi is greater than equals to minus d, right? And now we know that or is a TC0 circuit, right? Or can be computed. Just one threshold gate, right? Yes, well, this would look something like this. So TH gate for or, sorry, and, yeah, not or. So this gate can be at the top, and this has two inputs. One is TH1, one is TH2, where TH1 is uh, x1 plus up to, and TH2 is, yeah, so is this fine? So we get a circuit with three
Yeah.
size, three depth two, right? So size equals three, depth equals two. Yeah. Okay, so the next problem is ah, Okay, so over here they're given an n-bit number y in, uh, in binary, and we want to find a j such that y lies between 2 to the j minus 1 and 2 to the j, right? And we want to do this in NC1. And if you would recall, we needed something like this in the proof of division in log space uniform NC1, right?
Yeah, Beam
Yeah,
Cook Hoover.
right, yeah. So we needed something like this in that proof, right? So let's see how to do this. Okay, so so can you propose a very natural approach to do this? So when is it that y is between these two numbers? Okay, so when is it that y is between 2 to the n minus 1 and 2 to the n? So when is this 2?
Uh, Actually, in the theorem, some approximation is computed.
Oh yes, okay, so
So
this is
instead,
used to compute the approximation, right?
okay, okay.
Okay, so you find such a j and then use j to sort of approximate y as y tilde.
Yes, yes, yes.
Yeah, okay, so this you can do exactly. Okay, so let's look at some example. So let's say you have 111. Okay, and so this is a great. Okay, so 2 to the 2 is less than 111 is less than 2 cube, right? So this is a three-bit number that satisfies this.
Yes.
And you, so this happens when the first digit is 1, first bit is 1, right? Similarly, 2 square is less than equals to 1, okay, 1, 110, 2 cube. 2 square is less than 101, and 2 square is less than equals to 100, 2 cube, right? So whenever the first bit is 1, you get this, right? When the first bit is 0, this would be 2, 1 and 2 square, right?
Yes.
Right. So in general, using this, can you say when would this be true? So in general, when would this be true? Okay, let me do this first. So y is 2 to the n minus 1 times yn minus 1 plus 2 to the n minus 2 times yn minus 2 plus 2 times y1 plus 2 to the 0 times y0, right? So if I want y, okay, first of all, we know that y1, y is always going to be less than 2 to the n, right? Why? Because even if y1, y0 to yn minus 1 were all ones, the number would be 2 to the n minus 1, right?
Yes, yes.
So this we already know. So we know that j can only be in 0 to n minus 1. Okay, so yeah, this should be something like j in 0 to n minus 1. Yeah, because it can be 0 as well. Yeah, so j, we know that j is between 0 to n minus 1, right? Now, when is it n minus? Oh wait, no, no, no. I was right. Yeah, so j is in. So uh, yes, okay. So what's the smallest possible value of j? So y is uh, less than 2n, and y is also greater than 0, right? So the smallest that you can have over here is 2 to the 0, which is 2 to the 1 minus 1. And so j, the smallest value of j is 1. And the largest is, this is n minus 1. So yeah, the largest is n. Yeah. So Yeah, so this should be j in n. Okay, so y is the smallest value is 0, the largest value is 2 to the n. So now the question is, when can j be exactly n? So the question is, when is y exactly between 2 to the n minus 1 and 2 to the n? Is it possible? Is that possible when yn is 0? Yn minus 1 is 0?
No, no, no.
Right, because this can be at most 2 to the n minus 1, right?
Yes.
Yeah, so for j to be n, this yn minus 1, okay, let me write it. Uh, for j equals n, yn minus 1 must be 1, right? Okay, so what about j equals n minus 1? So for j equals n minus 1, can yn minus 1 be 1?
No, it has to be 0.
Right, so then yn minus 1 is 0. And what about yn minus 2? Can it be 0?
Uh,
Okay, so now this term isn't there at all, right? So if yn minus 2 were 0, then you would be left with a number which is 2n minus 3 minus, sorry, 2n minus 2 minus 1, right?
yes.
And that won't work, right? Because we want y to be at least 2n minus 2, right? So when you put j equals n minus 1, this would become 2n minus 2, right?
Yes.
Yeah, so we need this to be 1. And this sort of suggests a natural thing, right? So can you guess what expression we would have over here?
1 0, yn minus 2 0, and yn minus 3 1.
Right. Yeah, because any such number would be between 2 to the n minus 3 minus 1 and 2 to the n minus, wait, oh, any such number would be between 2 to the n minus 3 plus 1 minus 1 and 2 to the n minus 3 plus 1. Hmm. Yeah, so in this case, you would get what you want, right?
Yeah.
Yeah, and we can do this in general, right? Because over here it's minus 2, and over here it's the last thing is minus 3, right? So, and by n minus I minus 1 is equal to 1, yn minus I is 0, right?
Yeah.
Yeah. Okay, so now, so the expression is this, right? Okay, actually, now that we have this, I can write this. These are if and only, right? So, is this fine?
Yeah.
Yeah. Okay, so now I want to compute j, right? But j itself won't be a single bit, right? So j goes from 1 to n. So j would be a number. Okay, so let me write the exact expression over here. So we have n bits, so j goes from 1 to 8, so it's feeling equals, yeah, it's this. Yeah, so j is an, uh, oh no, no, not m, it's n. So j goes from 1 to n, so j will lie between, okay, so the number of bits that you would require for j would be floor log n plus 1, right?
Yes.
Yeah. And we want to compute each and every bit of j using an NC1 circuit, right?
Yeah.
Okay, so let's see how to do that. So, okay, let j be mm, j n minus 1 to j0, right? And we want to compute. So, we have this condition and we want to convert it into this, into something like this, right? So let me first write this condition in a slightly nicer way. So, j equals to b. So j equals n minus I. So the last one is this. So b minus 1. And this is the same as this expression. Yeah, so j is b if and only if this is true. And now we want to convert this expression into a circuit for each of these. Okay. So how can we do that? Okay, so here's one way to do it. Let me call this ZB. Okay. So compute this can be done in order n and depth per ZB. Okay, so now we have all the ZBs, and from that we want to compute the bits of J, right? So here's one way to do it. Uh, let define JB to be the wait, wrong. Wait, is it and? Yeah, I think it's or. Okay, so my claim is that, oh wait, okay, I'm using I for this. Okay, yeah, so I'm using B for this and I would use something else for the index. So let me say use JL. Okay, let me write it like this. For all L in 0 to define JL to be the OR of all B's such that the Lth bit of B is 1 Z. Okay, so my claim is this gives you the correct J. Okay, so first of all, is it clear what I'm doing over here?
No, actually, could you please explain again?
So starting from where? Over here
Yeah,
or
yeah,
over here?
that define
Okay,
J
okay,
JL.
right. Okay, so we want to compute J0 to Jm minus 1, right? And what I'm doing is that over here I'm saying that let's define JL like this. Okay, and what does this say? So we have this condition for all B, right?
Yeah.
And what I'm saying is pick all B's so that the Lth bit of B is 1.
Mm-hmm. Okay.
So let me say so let's say B was something like 0, 1, 0, 0, 0, 1 and L was 1. Then I won't pick B because the first bit, so I'm calling this the 0 bit, I'm calling this the first bit. The first bit of B is 0, right? So I won't pick B.
Mm-hmm.
On the other hand, if this were 1, I would have picked B. Okay,
Yeah.
right. So I am saying that I am going to pick all B's so that the Lth bit is 1. Okay, and then I'm going to put ZB over here.
Yeah.
Okay, now let's see why this works. So suppose JL was equal to B, right?
Yeah.
Then, okay, sorry, not JL. Suppose J was equal to B, right? Then this tells us that the only ZB which is 1 is exactly the ZB, right? With the same B. So out of all the ZBs, exactly one is 1 with the same B over here, right? So let's say J was 3, then Z3 would be 1, everything else would be 0, right?
Yeah.
Right. And now, so Z3, so what we have is Z3 is 1, and we want to output uh, a bunch of zeros depending on the M, and 1, 1, this is what we want to output, right? So is this fine?
Yes.
Right. Okay, so how can we do this? Okay, so look at what we are doing over here. We are picking all picking all B's so that the Lth bit of B is 1. Okay, so let me look at J0. So what would happen in J0? You would have odd all the B's so that the Lth bit of so that the 0th bit of B is 1, right? So in particular bit, we would have picked Z3 over here, right?
Yes.
And so J0 would be 1. Similarly, let's look at J1. What's happening over here? We are picking all the B's so that the first bit is 1, right?
One. Yes.
In particular, we would have picked Z3, and so Z3 would be over here, and Z1, J1 would also be 1, right?
Yes.
What about J2? We are picking all B so that the second bit is 1, so we would not have picked Z3, right? Because the
Yeah.
second bit is 0. Second, indexing from 0, that's right. The second bit is 0, right?
Yes. Yes.
Right. So I wouldn't have picked Z3. I would have picked other Z Ks, right?
Yeah.
But all of those Z Ks are 0 because J is 3, right? Since J is 3, only Z3 is 3. And so even if I pick other Z3s over here, this quantity would still be zero, right?
Yes.
And this happens for like every bit, right?
Yeah.
Yeah, so this would work, right?
Yes.
Yeah. So what we are basically doing is sort of, so we have, what we are doing is the following. We have B in binary, we are converting into unary in some sense. So what you have is you have these B options. So you have these options and you have a binary number, right? And you, depending on, let's say this is 3, and you want to pick the third option over here. So this circuit basically does this. So if you remember multiplexer from digital logic, this is something like the multiplexer. So is this fine?
Yes.
Yeah. Okay. So then let's look at the next problem. So the next couple of problems are about groups. So the uh, the group uh, Z cross P to the N has size P to the L minus to the L minus 1, where P is prime. Okay, so what is the group Z cross PN? So can you tell me the definition of this group?
Uh, I think this is a group of integers
Right,
of size p to the power l with the operation multiplication.
right. So you need one more thing. So it's is the set of, okay, let me do. Yeah, so it's this, right? It's a set of all numbers which are co-prime to P to the L, and the operation is multiplication mod P to the L, right?
Yes.
Yeah. Okay, so first of all, do you know why this is a group, or should I prove that?
Uh, I don't know this particular, but in general, I know the groups.
Okay, so in general, you know the definition of the group, right?
Yeah, yeah,
Okay,
yes.
so let me prove that this is a group. Okay, because yeah, I mean we are using this anyways for the proof of the theorem that division is the NC1. So let's prove that this is actually a group. Okay, so what properties do you need for the for something to be a group, right? Okay, so the first thing is, so what's the first property that you need for something to be a group?
Closure properties.
Right.
It should be closed.
Okay, so suppose A and B are in Z cross P to the L, and A, comma, okay, let me write it like this. So both of these are one, right? Because they are co-prime. And what do I want to show? So AB, let me call C. So let's say C is AB mod P to the L, right? And we want to show that C is in Z cross PL, right?
Yes.
So first of all, C is going to be in P to the L. Okay, let me write it more explicitly. So this is going to be true, right? Because they're going mod P to the L,
Yes.
right? And okay, I should write 0 over here. Why 0? Because C might be a multiple of, okay, AB might be a multiple of P to the L, in which case we might get 0, right? Okay.
Yeah.
Yeah. Okay, so now we need to show two things. Number one, that C is not 0 and that C is relatively prime to P to the L, right?
Yes.
Okay, so my claim is P to the L does not divide AB. Why? Because of this.
Yeah, because they both are co-primes.
Right. So if you factor out A and if factor out B, there is the P to okay, there is no P in the factorization, right? Anyway.
Yes. Yes.
So when you multiply A and B, you multiply the two factorization, there is no P in the factorization still, right?
Yes.
So P to the L cannot divide AB. So C is not equals to 0. Also, my claim is why? Again, the same reason, right? So if I multiply, okay, if I factor out AB, it is the factorization of A times the factorization of B. But since GCD of A and P to the L is 1, which means they do not share a common factor, that is, the factorization of A does not have P, and the factorization B of P also does not have P, right? The factorization of AB cannot have P, right?
Yeah.
And P is the only prime factor of P to the L, right?
Yes. Yes.
So there are no common prime factors between AB and P. So there are no common factors between AB and P to the L. So there are no common factors between C and P to the L, right?
Yes.
Yeah. So this is also one. So C is in the group. Or just said because I still haven't proved it's a group. And this satisfies closure, right?
Yes.
Yeah. What's the second property?
Uh, I think associative.
Right. And okay, we don't need to prove this because we know that a multiplication is associative, right? So multiplication mod P to the L would also be associative.
Yeah.
Yeah. So what we know is this, right? A times E times C. Okay, let me okay. A times P times C mod P. Okay, I can make it simpler. A mod P T L times B mod P to the L whole mod P to the L. So we know this is true, right?
Yeah.
And we know multiplication is associative, right?
Yes.
So what we can do is like in the associativity of multiplication, just put mod P to the L everywhere, right?
Yes.
And that would give us associativity for the group operation, right?
Yeah.
Yeah, so like this along with uh, product mod to the L. Okay, so what's the third property?
Uh, I think
Okay.
multiplicative inverse
So even before
uh,
inverse, you need something else,
or identity.
right? Because to
Identity.
define inverse, you need identity, right?
Yes, yes, yes.
Yeah. So can you guess what the identity of this group is?
Uh,
Okay, so okay, forget multiplication mod p to the n. What's the identity for multiplication,
one.
right? So let's so basically because this holds, that would also be the identity for multiplication mod p to the n. Okay,
Yes.
so yeah, a times one mod p to the n is a mod p to the n, and one times a mod p to the n is also a mod p to the n, right? So one is the identity. And what's the fourth property?
The multiplicative inverse.
Right. And this is slightly trickier. Okay, so what do we want to show? We want to show that there exists the
Such that AB mod PL is 1.
right. Yes, right.
Yeah.
Okay. And okay, so given A, what would B be? How do you show that such a B exists? And okay, so far in one, two, and three, we never use the fact. So it's over here that we need the fact that GCD is one.
Mhm.
Okay, so let me state the fact that it is. Yeah. So for this, to prove this, we need the following fact. For any, okay, I'm using for elements. Okay, let me do both right both for Z. Uh,
Okay, the linear combination is 1.
yes.
Yes, yes.
So we'll use this fact. Okay. And now, can you tell me how using this fact we can find a B? Oh, sorry, the linear combination is not one, it's GCB. Yeah. So can you tell me how using this fact we can find the GCB? So here we have X and Y. We have to somehow need instantiate X and Y for our case, right?
Yeah.
Yeah. So here's one way to do it. So here, from fact two, there exists R and S such that R times A plus S times P to the L equals to 1, right? Because the GCD of A and P to the L is 1.
Yes.
Okay, now let me go mod P to the L on both sides. So this implies R times A mod P to the L equals 1, right? Which implies R times A is just 1 mod P to the L. Calculate on this. Okay, so we have that R times A is 1 mod P to the L, and this also implies that A times R is 1 mod P to the L, right? Because the multiplication is commutative.
Yes.
So if R were in P to the R were in the group, we would be done, right?
Exactly. Yes.
So now we need to prove that R is in the group, right? So we need to show, okay, so R is clearly less than or okay, so R is between, okay, wait, not R. Yeah, because R can be an integer, right? It can be negative as well. So we need to show that B, which is equal to R mod P to the L, is in Z cross P to the L. So like over here, I can replace R by B, right? Because mod P to the L doesn't matter.
Yes.
Yeah. So we need to show that B is in Z cross P to the L, and then B would be the inverse of A, right?
Yeah.
So what from this we can say that B is less than equals to 0 and at most. So again, we need to show that B is not 0 and that yeah, B the GCD of B and P to the L is 1, right?
Yes.
Okay. So B is not 0 because 0 is not equals to 1 mod P to the L. Okay. Because A B equals to 1 mod P to the L would imply 0 is 1 mod P to the L, right? Which is false. So all I did was replace B by 0 over here, and that would mean 0 and 1 are the same mod P to the L, which is not true, right?
Yeah.
Yeah. So now we need to show that GCD of B and P is 1, right? Okay,
Yes.
so how do we show that? Okay, so we have this, right? A times B is congruent to 1 mod P to the L. What does this imply? This implies that A times B looks like, okay, I've used S, so let me say T times P to the L plus 1 for some T in Z, right?
Yes.
And this means, okay, so we have this, right?
Yeah.
Now, what do we want to prove? We want to prove that the GCD of B and P to the L is not 0, right? So, oh wait, no, okay, not 0, it's not P. Right. Wait, so,
No. We want to prove GCD of B and P to the power L is 1.
right.
Yeah.
Yeah, so another way to put it would be that it's not P. Okay, so it's not a multiple of, it's not a power of P, right?
Okay. Yes.
Yeah. Okay, so wait, can I just directly use this? Oh, wait, yeah. Yeah. Okay, so uh, pick any C that divides B and divides P to the L. Okay, my claim is C divides 1. Okay, it follows from, right. So is this fine?
Yeah.
Yeah, so because C divides this and this term, right? So C divides their sum. So C divides
Yes.
1, right?
Yes, yes, yes.
Yeah, but okay, so we also know that C is going to be greater than equals to 0.
Yeah.
Yeah, okay, pick any C. I should write pick any C greater than equals to 0 because we are looking for GCDs, right? Doesn't make
Yeah.
sense to use negative terms.
Yeah.
Okay, so let's do this. So, but what's the only C greater than equals to 0 which divides 1? It's 1 itself, right?
Yes.
So, what we have shown? We have shown that any common divisor of B and P to DL must be 1, and therefore that G, the greatest common divisor must be 1, right? So, is this fine? So, is this fine or should I explain this again?
No, this is fine.
Yeah. So, we also shown that GCD of D and P to DL is 1, so B is in, and we are done, right?
Yeah.
Yeah. In fact, this is something called an abelian group because the operator is also commutative, right?
Yes, yes.
Yeah. But yeah, we don't need that. So, okay, so that proves that this is a group. Now we need to show that its size is P to the L minus P to the L minus 1, right? That was the original problem. Okay, so okay, so any okay, so how can I construct Z cross P to the L? I can look at all the numbers from 1 to P to the L and just remove the numbers which are which have a common GCD with P to the L, right?
Yes.
So Z cross P to the L is equal to P to the L is set. So 1 to P to the L minus the set of all A such that is not equals to 1. Okay. But if the GCD of A and P to the L is not equals to 1, then P must divide A, right? Because what are the only factors of P to the L? So the only factors of P to the L are 1 and all the powers of P up to N, right?
Yeah.
Yeah, so if A and P to the L have a common factor, which is not 1, it has to be a power of P to the L. So P to the L, okay, it has to be a power of P. Let's say P to the K. So P to the K must divide A, and therefore P must divide A, right?
Yes.
So all I have to do is this set is the same as the set. Yeah, so the GCD of A, so P divides A, and A is less than P to the L, right? So A must look like B times P, with the smallest value of B being 1 and the largest being P to the L minus 1, right? Because if it were larger than P to the L minus 1, then A would be larger than P to the L, right?
Yes.
Yeah, so in the size, what is the size of this set? The size is P to the L minus 1, right? Because B goes from 1 to P to the L minus 1. And so size of is the size of this minus the size of this. Size of this is P to the L. Yeah. So is this fine?
Yes.
Yes. So the next one is sort of similar. Okay, so in the previous question we looked at Z cross P to the L. Now we are looking at Z cross N, right? We want to show that the size is P times 1, P minus 1 times Q minus 1. So first of all, what is the group Z cross N? Like what elements does it contain?
Uh, Maybe 1 to n. I don't know exactly.
Okay, so what was Z cross P to the L? It was all numbers between 1 to P to the L minus 1,
Which was
which were
co-prime to.
co-prime to P to the L, right?
Yeah.
So now all we have to do is replace P to the L with N. So this would look like uh,
So all
a,
numbers 1 to n which are co-prime with n.
yes. And the proof that this is a group is almost exactly the same as the proof that Z cross P to the L was a group. The only change would be over here. You would have to replace this by N. That's it.
Yes.
Yeah. So this is a group. We won't do this. And again, the operation is product mod N. Now we want to find out the size of this. Okay. So just like before, I can write this, right? Okay. So now we know the size of this set. If we find out the size of this set, we are done. So let me write. So is this fine? Okay, this is it only.
Yes.
Yeah, because
Because
the only factors of yeah, go on.
n is the product of p and q, which are distinct primes.
Right.
Yes.
Okay, so what do I have to do over here? Remove A. Okay, so this set, okay, let me write. Let me call this S1 and this S2. Yeah, so the set that we want to remove is the union of S1 and S2, right?
Yes.
And we want to find the size of that set. So we want to find S1 union S2, right?
Yeah.
So what is this size? So what is the expression of this in terms of the size of S1 and S2? So I want to write something like this.
Size of S1 plus size of S2
Okay.
uh, minus, I think, size of S1 and S2, intersection S2,
With
yes.
this, right? Yes. So we need to find all three sizes, right? So size, what size of S1? So any A in S1 looks like uh, let's say M times P, M in right. So any A in M S1 looks like M times P, where M is from 1 to Q, right? Why Q? Because if it were larger than Q, then A would be larger than PQ, right? Which is N.
Yeah.
Yeah. So size of S1 equals to Q. Yeah, it's the same as above, right?
Yes.
So what about size of S1 intersection S2? Okay, so from if something is in both S1 and S2, then P divides it and Q divides it, right?
Yes.
So what do these two tell you together? P divides A and Q divides A. They are both P and Q are distinct primes. Okay, so let's say you write down the factorization of P. It would contain P, right?
Yeah.
Okay, so S1 intersection S2 means that uh, A is in S1 and S2. A is in
Yes.
S2 means P divides A, and A is in S2 means Q divides A, right?
Yes. Yes. Yes.
So let's write down the factorization of P. Since P divides A, P must be the factorization, right?
Yeah.
Since Q divides A, Q must also be the factorization, right?
Yeah.
But that means P times Q is in the factorization, right?
Yes.
So that means PQ divides A, which means N divides A, right? But what's the only number between 1 to N that is divided by N? It's exactly N, right?
Yes.
And so the size is 1. Okay, so we know that the size of S1 union S2 is P plus Q minus 1, right? And size of N minus this, right? But what is N? N is PQ. So I can take P common from the first two, I get Q minus 1. Uh, well, they should be plus. Yeah, because minus 1 is plus. And I take a minus 1 common from the second. So I get this, right? And this is exactly what we wanted to prove, right?
Yes.
Yeah. Okay, so we have like 5 or so minutes. So let's quickly look at week 4's assignment since deadline is fast. And all the questions are mostly recall, so there is nothing to explain over here. So the first problem is, what is the optimal upper bound for the size of a ripple carry header for two n-bit numbers? Order n, order n square, order n log n, or order log n. So which of these is correct?
Order n.
Oh, the size of the ripple carry header is order n square, right?
Oh, okay. Order n
Yeah.
square.
So we considered three headers, right? Ripple carry. Uh, oh wait, no, no, wait. Okay, yeah. So
No,
okay, right. Yeah, the size of ripple
five,
carry is order n,
five n. Yes, order n.
right? Yeah. So we considered three things: ripple carry, uh, carry look ahead, and the one with prefix sum, right? So ripple carry had the optimal size, but its depth was bad, right? Which is the second question.
Y-
So what is
Yes,
the optimal upper bound of the depth of the ripple carry header? Order n square, order n log n, or order log n?
n square. Order n square.
Wait, is it order n square or order n?
Uh, uh,
The depth. So you can, okay, so what were we doing over there? After we had computed, let's say we had something like this, right? Let's say we had an to a0 plus bn to b0. And suppose we had, then what we were doing to compute an, we first had to compute this sum of a0, b0, look at the carry, a1, b1, look at the carry, and so on, right?
yes,
So the depth is just order n, right? Because you need one depth for b0, a0. Okay, this should be n minus 1 because n bits. Yeah, so you need one depth for b0, n0, b0, a0, another for b1, a1, one more for b2, a2, and so on, right?
yes,
So the depth is order n. Yeah, so the ripple carry header has the optimal size, but its depth is terrible, right?
yes.
Yeah. So then we constructed the carry look ahead header, right? Towards the optimal upper bound on its size, order n square, order n log n, or order log n.
Here also, I think order n.
No, no, no. So over here, the size is order n square, but its depth is much better than order n.
Okay.
Yeah, because over here, what were we doing for uh, AI, for let's say for computing AI plus VI, we were computing the carry for the carry CI in all the CIs in parallel, right? So we were computing C0 again, C1, C2, C3, and so on, right? To
Yes,
compute C0, you need order 1 penny gates. To compute C2, you need order 1 plus order 1, right? Order 1 for C1 and order 1 plus for A2 plus B2, right?
yes,
So for C2, C1 you need, C0 you need order 1, C1 you need 2 times order 1, C3 you would need 3 times order 1, and so on. So you would need order 1 plus 2 times order 1 plus 3 times order 1 plus all the way up to n times order 1, right?
okay,
So that's order 1 times 1 plus 2 plus 3 up to n, which is order n square, right? So is this fine?
yeah.
Yeah. Okay, so now what is the optimal upper bound on the depth of the carry look ahead header? Order n square, order n log n, or order log n?
I think order log n.
Right. So in the ripple carry header, the size was optimal, depth was bad. Now we have constructed a circuit where the depth is optimal, but the size is bad, right?
Yes.
And that's why we look at the parallel prefix sum header. So what is the upper bound on the depth of the parallel prefix sum header? Order n square, order n log n, or order log n? So which is true? Okay, so this had both the optimal size and the optimal depth, right?
Yes.
Yeah, so the optimal depth is order log n. Because if you want to read like n numbers, you need a tree of at least order log n, right?
Yes. Yes.
Yeah.
Yes.
And what is optimal upper bound on
Op-
the size of the, yeah, you were saying something?
order n.
Yes. So over here, both are optimal, right?
Yes.
Yeah. The next one is, what is the optimal upper bound for the depth of a circuit for multiplying two n-bit numbers? Order log n, order n, order 1, order log n square. So which of these is correct?
Mm, order log n square.
It's order log n.
Order log n.
Okay, so multiplying two n-bit numbers is equivalent to like iterative addition of n many numbers, right? N many n-bit
Uh,
numbers.
yes, yes, yes.
And the depth required for iterative addition of n many, sorry, m many n-bit numbers is order log m plus log n, right?
Yeah.
So it's in our case it's order log n plus log n, order 2 log n, which is order log n.
Yes.
Yes. You know what's the optimal upper bound for the depth of a circuit computing the dot operator as defined in the context of a parallel prefix sum adder circuit? Order log n, order 1, order log square n. So which of these is correct?
Uh, I don't know the answer.
Okay, so let's just recall what that operator was. So it took three inputs.
Okay, okay. CP. Yes, yes, yes.
Okay, so this clear was always clear, generator was always generate,
And
and
second
this, oh
CPG.
yeah, CPG. Right. So now it doesn't matter what the truth table is. It so this takes constantly many inputs, right? It just takes two inputs over a domain of
Yeah,
size 3, right?
yeah.
So you can replace like let's say C by 0, 0, this by 0, 1, this by 1, 0. So you have like 4 bits and you want to output 1 bit. So this you can do in constant depth, constant size, right?
Yes.
And so both the depth and size are order 1.
Yeah.
Yeah. Okay, so that's all the questions that we had for today. So if you don't have any other questions, we can like end the meeting today and meet next week.
Yeah.
Okay.
Thank you.
Yeah. Thanks. Bye.